They were having problem at NASA in that time.
Mm-hmm.
So NASA became the managers of the program, not the actual designers.
A NASA employee thought it would be a routine data check, but when the James Webb Space Telescope stared deeper into space than ever before, something unexpected appeared. Galaxies that shouldn't exist, structures forming too early, signals that defied explanation. In that moment, it became clear Webb had looked too deep, and what it found was shocking. Galaxies that shouldn't exist. That first deep field image was supposed to be a simple demo, a proof of concept. Instead, it became a scientific gut punch. Scientists started counting galaxies, then recounting, then checking again. Thousands of entire galaxies appeared in a single frame, each one holding billions of stars, all squeezed into a tiny slice of space. And hidden among them were warped arcs of light, stretched shapes caused by gravity bending distant galaxies like cosmic funhouse mirrors. That wasn't an error. That was gravitational lensing doing its thing, turning massive foreground clusters into natural magnifying glasses. Thanks to that effect, Webb was showing galaxies that existed over 13 billion years ago. But here's the problem. Some of them looked way too bright, too organized, too evolved. These galaxies weren't supposed to have had enough time to form stars, build structure, and develop heavy elements. Yet there they were, already acting like mature systems. That forced astronomers into uncomfortable territory. Were galaxies forming faster than physics allows? Were early conditions wildly different? Or were our timelines just wrong? And this wasn't from months of data. This came from a snapshot. In just hours, Webb rewrote our map of the early cosmos and made it painfully clear that empty space isn't empty at all. Alien atmospheres finally decoded. Webb wasn't built only to stare into the ancient universe. It was also designed to look closer at planets orbiting nearby stars. Before this, finding exoplanets mostly meant watching shadows. A planet would pass in front of its star, light would dip slightly, and astronomers would make careful guesses. It worked, but it was limited. You could tell a planet existed, maybe estimate its size, but that was it. Webb changed that by doing something revolutionary. It began reading actual atmospheric chemistry. Instead of silhouettes, scientists could now split starlight passing through alien skies and analyze it wavelength by wavelength. That's how carbon dioxide was detected on WASP 39b. Then came water vapor on multiple worlds, methane, sulfur dioxide, even clouds made of tiny glass crystals floating through scorching atmospheres. Let that sink in. We're talking about planets hundreds of light years away, and Webb is telling us what their clouds are made of. Some of these worlds are boiling gas giants. Others cling tightly to their stars. None are friendly. But that isn't the point. The point is, we can finally read them. For the first time, exoplanets stopped being shadows and started becoming real places with weather, chemistry, and personality. And that quietly opened a whole new chapter in how we search for life. Our solar system revisited. After blowing everyone's mind with distant galaxies and alien planets, Webb did something unexpected. It turned around and looked closer to home. And somehow, it still managed to surprise us. It delivered the sharpest view of Neptune in decades, revealing cloud layers, temperature differences, and even details around the planet's poles. Then it locked onto strange objects like Cheroklo, a small asteroid with its own ring system, and detected water ice on its surface. That's an object only a few hundred kilometers wide, and Webb was mapping its chemistry. Then came Europa. Scientists had long suspected this icy moon of Jupiter was venting water into space. Webb confirmed it, catching plumes of vapor shooting out in real time. That means Europa isn't just frozen, it's active, leaking material from a hidden ocean beneath its crust. Even comets got their moment. Webb analyzed one inside the asteroid belt and found water, but no carbon dioxide, which is unusual. That tiny detail tells us something important about where it formed and how water might have spread through the solar system. It didn't stop there. Webb also detected organic molecules on distant icy bodies beyond Pluto. These weren't leftovers from a dead system. They were chemical archives, quietly preserving the story of how our planetary neighborhood came together. The too early, too big galaxy problem. By 2023, Webb's deep surveys started pouring in, and astronomers noticed something unsettling. there were too many galaxies. Not faint smudges, not barely there blobs. Fully formed galaxies showing up within the first few 100 million years after the Big Bang. Some appeared just 235 million years after everything began. That's absurdly early. To build a galaxy like that, you need generations of stars to live, die, and recycle material. You need dust, gas, gravity, and rotation working together over long stretches of time. But these galaxies didn't have that time, yet they looked complete, bright, compact, structured. Astronomers started calling it the too early, too big problem. These systems were massive, luminous, and actively forming stars at rates that made no sense given the limited ingredients available. It was like watching a bonfire erupt before the wood had even dried. So theories started flying. Maybe star formation was more efficient back then. Maybe dense, early conditions sped everything up. Or maybe galaxies formed through rapid, direct collapse instead of slow assembly. Whatever the answer is, Webb made one thing clear. The early universe wasn't quiet. It was loud, crowded, and moving at a pace no one expected. Black holes that grew too fast. Once astronomers realized galaxies were growing unusually fast, another question followed immediately. Where were the black holes? In today's universe, most large galaxies host supermassive black holes at their centers. But those monsters are supposed to take time to grow. Webb showed they were already active when the universe was less than 600 million years old. That's a serious problem. Black holes need material. They need stars to die. They need galaxies to evolve. All of that takes time. Yet Webb spotted galaxies from the early cosmos with clear signs of feeding black holes, pulling in matter and lighting up their surroundings. Some were so bright they had to be magnified by gravitational lensing just to be seen. This revived a controversial idea: direct collapse black holes. Instead of forming from stars, some may have formed straight from massive gas clouds, collapsing almost instantly into enormous objects. Webb also caught lensed supernovae appearing multiple times across space, offering new ways to measure cosmic expansion and revisit the ongoing Hubble tension debate. And then came another surprise. Webb found galaxies that had already stopped forming stars entirely, just 700 million years after the Big Bang. Sleeping galaxies and cosmic asymmetry. Just when astronomers thought Webb couldn't get any stranger, it started finding galaxies that were already done, not forming stars, not growing, just sitting there. These galaxies showed up less than 1 billion years after the Big Bang, already quiet and inactive. Scientists call them quiescent galaxies, but the nickname that stuck was Sleeping Beauty galaxies. They burned bright early, used up their fuel, and shut down fast. That's not how galaxies are supposed to behave. Normally, galaxies go through a long, messy phase of star birth, gas clouds, and chaos. But these looked like cosmic retirees showing up in kindergarten. Too mature, too early. Then Webb revealed something even more unsettling. When researchers analyzed galaxy rotations in deep field surveys, they noticed a strange imbalance. More galaxies appeared to spin one direction than the other. That challenges a core assumption in cosmology, that the universe looks the same in every direction. Some scientists think it could be observational bias. Others wonder if there's a deeper structure baked into space-time itself. Either way, Webb forced another uncomfortable realization. The universe might not be as uniform as we assumed. And those early galaxies, they weren't just forming. They were living fast, dying young, and rewriting cosmic expectations. Possible signs of life and direct planet images. Then, in 2025, the conversation shifted from structure and timing to life. Webb examined a distant planet called K2-18b and detected a mix of molecules that made scientists pause: methane, carbon dioxide, and most intriguingly, dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by living organisms, mainly marine plankton. Now, this isn't proof of aliens. Scientists were careful about that. Exotic chemistry could still explain it, but the signal was strong enough to matter. For the first time, we had real data suggesting biological processes might be possible beyond our solar system. Around the same time, Webb also achieved something historic: its first direct image of an exoplanet. Not a shadow, not a dip in starlight, actual photons coming from another world's atmosphere. Scientists could measure temperature, cloud layers, and molecular fingerprints directly. That's a massive shift. Planets stopped being abstract statistics and started becoming physical places. And when you combine that with distant galaxies, early black holes, sleeping star systems, and strange chemistry in alien skies, one thing becomes clear. James Webb isn't just observing the universe, it's forcing us to rethink nearly everything we thought we knew about it. So, if James Webb really looked too deep, what do you think it uncovered out there in the dark? Let us know in the comments below.